Hi folks, Bill of the North here. I just wanted to do a quick overview of how to use the Nautical Almanac. I'm self-taught in celestial navigation, and really one of the hardest things for me to learn was just how to use the Nautical Almanac and look things up in it and do the formulas. So I'm going over that real quickly. Like I said, I'm self-taught. There may be gaps in my knowledge or things that I learned incorrectly. So hopefully you'll politely point it out if you do notice something like that. I'm also not going to go into any definitions or theory because hopefully you're beyond that if you are at this point now. Now inside the almanac is this form which shows you how to do a sight reduction, and it has all the information and the rules on it that you'll need, although the language is kind of a terse mathematical thing which can be hard to understand, but once you know what it means, they're good reminders. Now I've already taken my sextant shot on the sun, and it's March 17th, 2015, and I did it at 2100 hours, 9 minutes, 28 seconds UT time, which is also Greenwich time. I've already taken my sextant shot of the sun, and I've done my corrections to it, so that gives me 26 degrees, 6 minutes. As you know, you pick an assumed position that's close to your estimated position, and your latitude has to be a whole degree, so I've picked 43 degrees north, which is very close to my estimated position. My longitude is 84 west, and that's an assumed longitude, and I know it's going to change later. The bulk of the Nautical Almanac consists of the daily pages, and they're made up of 3 days with columns for the planets, the stars, the sun, and the moon. Now, since I shot the sun, I'm going to go to that column. You'll notice on the left there's a column for each hour of UT time, or Greenwich time. That's not your local time. There are 2 more columns below the sun. One is for the Greenwich hour angle at the top of the hour, and the other is for the declination at that time also. Now I took my shot of the sun at 2100 hours and some minutes and seconds, so I moved down to 2100 hours, and that gives me a GHA of 132 degrees, 55 minutes, and 4/10. To the right of that is my declination of the sun, and as you'll note, it's in the south. This one actually carries down to in front of all of those columns, so that gives me a south declination of 1 degree, 12 minutes, and 9/10. Now, if you notice these numbers, they're getting smaller, and we are going to have a correction to the declination. So the fact that those numbers are getting smaller means that we will subtract that correction. If the numbers were getting larger, we would add it. Now at the very bottom of the page, at the bottom of the declination column, you see that small case D. The number 1.0 next to it indicates the hourly change in declination. In this case, it's 1 minute per hour. We're going to use a fraction of that later on to correct our declination. Now we have our GHA for 2100 hours, but we actually took our shot at 9 minutes and 28 seconds after the hour. So we turn towards the back of the Nautical Almanac, and we find one of these pages labeled Increments and Corrections. And we're going to find the page for 9 minutes. Immediately below our 9 minutes are seconds, so we simply go down to our 28 seconds. The column to the right of that is for the sun, so that means we are going to add 2 degrees and 22 minutes and 0/10 to our GHA. This is where we look up the value of our correction for declination. Those 2 columns labeled V or D, we simply move down till we find the value that we had looked up, that small case D, 1.0, and we move to the right. 0.2 is our actual correction value. Now there's our declination, 1 degree, 12 minutes, 9/10, and we're simply going to subtract 2/10 from that. That will give us 1 degree, 12 minutes, and 7/10, which we might as well just round up to 1 degree, 13 minutes. Next we add up the GHA and the increment. So that's 132 degrees, 55 minutes, and 4/10, plus 2 degrees, 22.0 minutes. That gives us a total final GHA of 135 degrees, 17 minutes, and 4/10. Our next step is to add or subtract our assumed longitude with our final GHA. In the Eastern Hemisphere, you add. In the Western Hemisphere, you subtract. Since we are in the Western Hemisphere, I'm going to subtract that west assumed longitude from my final GHA. But there's a wrinkle. LHA has to be a whole degree. So that means I have to change my assumed longitude. I'm simply going to move down that 17 minutes and 4/10 to my assumed longitude, and that gives me an LHA of 51 degrees. The site reduction tables are towards the back half of the book. To use the site reduction tables, we simply move along this column to the right where it says lat/A till we find our assumed latitude. In our case, our assumed latitude is 43 degrees. Now, at this point, we're going to look up three sets of numbers, A, B, and Z1. The other number that we need is our LHA of 51 degrees. If you notice those two left columns there, those are both LHA and they run up and down the left side of the page. On the right side of the page there are also two columns for LHA. You simply find the column that has your number and you use that. Our LHA was 51 degrees, so we simply move to the right to the column for 43 degrees latitude. And we get our three sets of numbers. A is 3438, B is 3401, and Z1 is 49.9. Now on A, you may notice that I have underlined 38 minutes. And that's a reminder to myself that any minutes over 29 degrees are rounded up for the next whole degree for some of the functions. Now that only applies to A, F, and P. Now we're going to subtract our declination from B, and that gives us 32 degrees and 48 minutes. You'll notice I underlined 48 minutes on F. Later on, we're going to round that up to 33 degrees. Now for our second run through in the site reduction tables, we're going to take the value of A, which we've rounded up to 35 degrees. Using the same column we used to look up LHA, we just find our value for F, which we rounded up to 33 degrees.
So there are our three numbers. H is 2630, P is 5008, and Z2 is 69.6. Now there are the numbers we got for H and P, and H is 26 degrees 30 minutes. P is another one of those numbers that you might have to round up, and I've underlined the 08 there. In this case, though, being smaller than 29 minutes, we don't have to round up. Now all those numbers labeled with a Z have to do with our azimuth, so I'm going to add Z2 and Z1 together, and that gives us Z, which is 119.5 degrees. But there's a rule that applies to that. Our LHA was 51 degrees, and there's a rule that applies for LHA smaller than 180. And that rule is that we subtract the value of Z from 360 degrees to get Zn, which becomes our true course azimuth. In this case, 240.5 degrees. So we'll probably just round that up to 241 when we plot it.
Like I said, each corner in the site reduction table has a set of rules. Just check them and see if they apply to you in your particular instance.
Now we have two corrections that we have to do to H, and that's what we're going to do next. This is the first correction, and we take F's minutes, which were 48 minutes, and we take P's whole degrees, 50, and we're going to find the intersection of those two columns, and that will give us our correction. If F's minutes are between 1 and 29, this correction will be a positive. And if it's between 30 and 59, the correction will be a negative. In our case, it's 48, so it's going to be a negative correction. We follow the 48 column down to where it intercepts 50, and we get our correction. In this case, we subtract 9. For our next correction, we use A's minutes and Z2's whole degrees. And this will be a negative correction if A's minutes are between 1 and 29, and it'll be a positive correction if A's minutes are between 30 and 59. In our case, A's minutes are 38 and Z2's whole degree 69. So our correction is +8. All right, so we take the value of H, 26 degrees, 30 minutes, and we subtract 9 minutes from that for the first correction. For the second correction, we add back 8 minutes, and that gives us an HC of 26 degrees, 29 minutes. Now we take HC and HO, and we subtract the smaller from the larger. In this case, HC is larger, and that gives us a result of 23 minutes. Now we're going to plot our line of position crossing our azimuth at some point, but where do we plot it? Well, that's where the difference between HC and HO comes in handy. And we've determined that that difference is 23 minutes, which is about 23 nautical miles. But which direction? Well, you see the A and the T. Whichever one is the larger number determines which direction. In our case, it's A, which means away from the sun. So from our assumed position, we're going to plot along the azimuth 23 miles away, and that's where we will put our LOP, our line of position. Here's our plotting sheet. I've already labeled it as 43 degrees north latitude and 84 degrees west longitude. Now we find the point of our assumed longitude, which is west, 84, 17.4, and we plot our azimuth. That's marked for the sun, 241 degrees, and the date. Now our line of position will cross our azimuth at a 90-degree angle, and this is where the difference between our HC and HO comes in handy. So right here is where our line of position will cross our azimuth. We simply draw a line right there. So here is our line of position. And if we've done everything right, we're somewhere on that line. To determine your exact position, you would do this at least 2 or 3 other times, and where the lines of positions cross, that's where you're at, or close to it.